Welcome to this session of my presentation. Good morning, good afternoon, good evening, wherever you may be in this part of the world. And my presentation title is Generator Protection. And my name is John Kweku Amo Otu, and I've been a professional electrical engineer for about 30 years, and I'm based in the United States. Okay, so this generator protection presentation is actually total number of slides is about getting close to about 600. So I've broken it into several different sessions. So this session will focus on the first session of generator protection. So there's going to be about 10 of these sessions that I'll make a presentation on generator protection. So this session is going to comprised of I'll talk about generator and its components as you see it in a typical power plant, and I'll also talk about ANSI nomenclature for generator protective relay. As you know, protective relay engineers basically speak in numbers. Our jargon is based on numbers. So if protective relay engineer says 87, definitely you know what he's talking about. He's talking about differential protection. So we'll talk about ANSI designated nomenclature that is basically designated for generator protection elements. Then we'll talk about pictures. Basically, I'll show you pictures of typical faults that we see in generator windings. Then we'll talk about typical generator connections that we see in power plants and industrial facilities. Then finally, for this session, we'll talk about different grounding schemes that we have for generators. Okay, so this slide shows you a typical picture of a small-sized based generator. So as you can see over here, you have a small-sized generator with a generator enclosure. And this duct shows you where air passes through to cool the stator winding. Then on this side is the rotor. So basically, the rotor basically carries the magnetic field. And the magnetic field it's what basically induces voltage into the stator. So on this rotor, basically it's the extension part. So this is a small sized generator on itself that helps to generate the DC voltage that is fed to this rotor. Next is another picture that shows you a bigger size picture that shows you the rotor that has been taken out of the generator stator. So as you can see over here, the rotor windings are embedded in slots in this region of the rotor, and basically this is basically the mechanical shaft that is coupled to the turbine shaft, and this is the end ring area, and cooling is also achieved through ducts on the various sections of this axial length of the rotor. This is a much bigger picture of basically a larger generator. Actually, this generator is rated at 650 megawatts. As you can see, this is a big generator. So as you can see, these are the turbine sections. As you can see, these are all the turbine piping basically that allows steam to be able to go to different sections of the turbine. So you can have the high pressure section here, intermediate pressure section here, and the low pressure section here. So basically the high pressure steam, basically that's part of the steam, the content, has it's about, I would say, about 90% dry steam, and very flowing at a very high pressure. So that is why they call this area high pressure section of the turbine. So the turbine blades on this side are basically are much smaller in size. So as you progress to the intermediate section, the turbine blades are basically increased in size. Then on the low pressure section, basically the turbine blades are much larger. So on this side is basically where the generator is located. So the generator is located at the farthest end. Next is another picture from a different angle of the same generator, 615 megawatts generator. So as you can see, and much closer, these are the different sections of the turbine. So the mechanical power is basically generated in this section. So you have the steam that is flowing through various sections of this part of the turbine, basically to generate the mechanical power. And the shaft of this turbine is coupled to the shaft of the generator rotor, and basically the mechanical torque is developed, and it converts to electrical torque. And so that is what drives the generator to generate electricity at the output of the generator. Next, it's other component of the generator that I showed to you in the previous slide. Okay, so remember, I showed you that we have a rotor. Basically, a generator consists of a stator and a rotor, right? So the rotor is the rotating piece of the generator. The stator is the stationary piece, right? Okay, so the rotor, as I indicated, is fed with a DC voltage and current from an extension system. So as you can see over here, this is a starter excited system of extension. So that is where the DC voltage and the DC current is fed through these brushes. So you have a slip ring here, and you have these brushes. So that is what feeds the voltage and the current. Basically, it feeds the voltage, and as a result, current is generated and is fed to the winding of the rotor to create the magnetic field. So that is what creates the revolving magnetic field, and the revolving magnetic field, as it rotates, it's able to cut the stator winding, and that is how it induces voltage into the stator winding. Next, we'll talk about ANSI nomenclature. Like I indicated, that protective relay engineers speak in jargons in terms of utilizing numbers to talk to each other. So we'll go through the ANSI designated numbers that we use for generator protection. So ANSI device number 40, right, is loss of field. Okay, so loss of field is, let's say you have a magnetic field that is set up on the rotor winding. So if you lose the extension system, basically the setup of the magnetic field is going to change. So that's how this relay ANSI device 40 detects a fault due to extension system by changing impedance based on the setup of the magnetic field on the rotor. Next is ANSI device 64F, and that is a field ground on the rotor. Okay, let's say if there's a turn-to-turn shock on the rotor, it is this relay that detects the fault, 64F. Next is phase distance relay, and that is ANSI device 21. If you have an external fault, let's say in the system, in the AC grid, right, and this ANSI device relay 21 is basically a backup relay for the generator differential protection. So the amount of contribution from the generator towards that AC grid fault, external fault, is detected by this phase distance relay. So as you can see over here, this is also based on impedance. It's an impedance-based relay. So it utilizes CTs and VTs, voltage elements, to basically calculate, the impedance. And also, it is made in such a way that it sees basically, it's more directional. Basically, it's pointing towards the generator as well. Next, it's ANSI device 24, and that's volts per hertz, right? So if a protective relay engineer says that, okay, ANSI device 24, definitely, I know it's a volts per hertz relay. So what this relay does is basically, its goal is basically to determine an overexcitation condition. And how does an overexcitation condition occur? It occurs, let's say, if you have a problem with the excitation system, and basically, it leads to higher voltage, at a generator terminal. Or let's say you have a loss of sensing of voltage through instrumentation, and also you have a load rejection on the grid. from other generators, so that can cause basically over voltage condition. And also, we have a frequency element in it. It's a V over F. So the V stands for voltage over frequency. So for frequency, if you have a heavily loaded generator, you can have in the AC grid here, you can have a drop in frequency, and that can affect the volts per hertz setting as well. Next is ANSI device 60FL. So that is fuse loss, right? Okay, so basically, you have VTs that are basically installed at the terminal of the generator. And basically what this VT is to basically sense the voltage measuring parameters of the generator. So on the high side of the VTs, you have fuses that basically protect the VTs. So if you basically have a fuse failure, right, then basically this relay is going to sense that unbalance of voltage and basically affect its output to trip the generator. Next is 50 BF and 50N. Okay, so this instantaneous element. So like I indicated, protect relays talk about numbers. So 50 BF means instantaneous breaker failure, and 50N is instantaneous neutral measuring elements. So these this relay basically, if let's say there's a breaker failure, let's say if a relay sets an output and it's supposed to trip the unit breaker and it fails, right? Then after a period of time, that is when this relay senses that if there's still current flowing through the breaker, and from there it starts time to activate to basically trip other breakers that are in close proximity to the unit breaker that is supposedly to be tripped. Next is 27TN, and 27TN is basically the 10 harmonic relay, under voltage 10 harmonic. 27 means it is under voltage relay. So what it does is this relay is utilized to complement high impedance grounded relay 59J or 59N that is located basically detects ground faults at the stator. So because the 59J relay or 59N relay can only detect ground faults all the way up to about 95% of from the generator terminals all the way up to the neutral. So the remaining 5% is not protected. The 59G or 59N relay cannot detect ground faults on the remaining 5%. So we utilize the 10 harmonic neutral under voltage to complement and basically cover the remaining 5%. Next is 87G. When the protected relay talks about 87G, he's talking about generator differential protection, right? Specifically for the generator. So basically this type of protection scheme has basically CTs are the terminals of the generator and CTs are the neutral of the generator. Basically what it's doing is basically measuring the differential in current based on Kirchhoff's law. That is what comes in, the same current must come out. So if there's any difference, an appreciable difference based on a minimal threshold, then basically that indicates an internal fault. Then we have 87U. Okay, so when do we utilize 87U relay? 87U relay is utilized when basically you are protecting a combination of the generator and the step-up transformer. So 87 differential relay excuse me, protects both the generator and the step-up transformer. Next is 59. 59 means an overvoltage relay. So you can utilize 59 for each phase that you protect. Next is over and under frequency. So you can have these are frequency elements that basically protect the turbine side of the turbine generator. So basically 81O is over frequency protection, and 81U is under frequency. That is we have a threshold of under frequency set point that the turbine is supposed to operate, and beyond that basically then that is when the 81 under frequency element relay kicks in. Then likewise, for over frequency, we also have a threshold, and these thresholds are basically provided by the manufacturer. There's a chart that the manufacturer provides that tells you the operating regions and the allowable frequency that you're supposed to have. And if you go beyond the time that you're supposed to operate before you take the generator out of line. Next is 32, and this is more of directional power. Let's say if you have a reverse power, you have a reverse power flow into the generator. And if you have a reverse power flow into the generator, then basically the generator basically converts from being a generator to a motor. So this is when this relay basically detects that reverse directional power flow. Then next is 59N element. Like I indicated, we utilize the 59N or the 59 chain through a high impedance grounding scheme. For most of the large generators. Like an example being the 650 megawatts generator that I indicated. So we utilize basically a single phase distribution transformer at a neutral, install it at a neutral, and basically derive a neutral from there, and we utilize this relay that is connected across a resistor, and the resistor is sized based on the stray capacitance from the generator terminals. Next is a typical setup of the generator protection elements for a generator for a typical power plant. All right, so as you can see over here, this is the connected utility system. So the AC grid is on this side, right? Okay, so this is the unit breaker, and its ANSI nomenclature is 52. So anytime you use the word 52, then we know that you're talking about a breaker or a unit breaker. So this is the generator step-up transformer. This is what steps the voltage from the terminal voltage of the generator to a higher voltage. So let's say you have a typical generator that has an output voltage of 30.8 kV, right? And you step it up to 230 kV or 345 kV. This is basically implemented by this generator step-up transformer. It steps the voltage up from 30.8 kV to 230 kV or 345 kV based on the desired voltage that you need on the transmission end. Okay, so for the protection scheme of this generator step-up transformer, right, as you can see over here, we have a 51N element and a 50N. So this is an instantaneous neutral overcurrent protection, and this one is a time neutral overcurrent. So this basically acts instantaneously, and this one basically operates based on an inverse curve. Next is all these basically protection relays can be a multifunction digital relay, a microprocessor relay, right? Okay, so you can have all these protective element as a single relay. So we have the 81O, like I indicated. This is basically this relay basically operates based on over frequency of the generator. When the generator is basically, the turbine generator is operating on over frequency condition. And what is an over frequency condition? Let's say the generator has a nominal frequency, operating frequency, right? Like 60 hertz, right? Okay, so the manufacturer will allow you to go beyond that. Let's say 60.5 hertz or 61 hertz. Beyond that, then basically, operating beyond that is going to be timed, and after that, you're supposed to trade the generator. Similarly, for 81U, which is the frequency element, let's say if you have a 60 hertz nominal operating frequency of a generator, let's say the manufacturer is going to allow you a tolerable range of 58.5 hertz to 60 hertz. Beyond 58.5 hertz, definitely the manufacturer will put a timing in it and basically trip the generator offline. Next is 59, and this is an overvoltage element. And let's say if you have an overvoltage condition at the terminal of the generator, due to a load rejection or due to inappropriate operation of the extension system, basically, or due to inaccurate sensing of voltage, then this is the protective relay that will sense it. 24, it's volts per hertz, and basically it's measuring voltage and basically dividing it by the frequency, and its goal is to basically to prevent overextension of the generator and the generator step-up transformer, because overextension can cause saturation of the core of the generator and the transformer as well. Next is 50 BF, and like I indicated, 50 BF is a breaker failure element. Basically its goal is basically, let's say if this relay element is supposed to trip this unit breaker, right, and it fails to trip it, then that is when this relay senses current flow through this breaker. When it senses that current flow after a period of time, then it knows for sure that this breaker has not tripped. Then it's going to time out and basically activate other breakers that are in close proximity, especially breakers that are on the AC grid, to trip it, to prevent the flow of evolution and cascading of from current flow into the AC grid. Next is 60 FL, and that is fuse loss. So what it's doing is basically the fuse that is connected on the high side of the VT, located at the terminal of the generator. Basically, what it does is, when the fuse goes out, it detects that unbalance of voltage measurements. Next is a loss of extension, and this is impedance-based protector relay measurements, and basically it's based on the setup of magnetic field on the rotor, right? Okay, if let's say there is a fault on the rotor, or there's a fault somewhere in the stator, right? Basically, this relay detects the change in the magnetic field, and it detects the change in the magnetic field based on changing impedance, and it's able to trip the required breaker. Next is directional reverse power flow. Let's say if you have a reversal of power flow into the generator from the AC grid, right? Then this generator is going to basically convert from a generator to a motor, and you don't want that. Basically, it's going to cause heating and a failure of the generator. So that is when this relay detects that reversal of power flow from the AC grid. Next is ANSI device 21, and this is a distance protection. This relay basically acts as a backup to the main differential protection, and basically what it's looking is basically it detects the contribution of the generator contribution to a fault in the AC system. Next is 27. 27 is basically an under voltage relay. Let's say if you have heavily loaded generator, basically the voltage is going to go down, or inaccurate sensing of voltage, then this is when this relay sets in and basically trips the required breakers. Next is 27TN. This is a 10 harmonic under voltage relay, and it complements 59N. Like I made mention that 59N stated ground fault relay is made to see only 95% of the stator winding, right? So the remaining 5%, this relay does not see and does not cover that region. So you need another relay to complement that protection. So that is when the 27TN complements the remaining 5%. But in fact, they set it in such a way that it overlaps. It covers about the last 10% of the neutral of the generator by creating an overlapping zone. Next is it's another multifunction digital relay type 1, and basically, so it all depends on how much cost you want to put into these microprocessor relays and the number of elements that you're going to have. So this is a type 1, this is a type 2, and type 1, these are all the elements that it has, and the type 2, these are the elements that it has. So the next element is 87G. This is the differential protection. This is the main protection system for the generator, right? So basically, you have CTs at the terminal of the generator and CTs at the neutral of the generator. So basically, it's measuring the difference in current. Next is 64F, and this is basically the rotor field ground relay that detects faults on the rotor winding, and if there's a 10-to-10 short, on the rotor or field winding failure, this relay is the one that basically detects and trips. And I made mention about high impedance grounding, right? This is the single phase distribution transformer that is utilized to achieve the high impedance grounding. Basically, what it does is it limits the ground fault current to about 5 to 20 amps, to prevent damage into the stator winding and the stator core. Next, we'll also talk about ANSI device numbers. So this basically shows you, all the applicable relay elements that form the generator protection, right? Okay, so I made mention of distance relay, ANSI device 21, force per hertz, ANSI device 24, and sync check, ANSI device 25. We utilize that sync check. Let's say if we bring in the generator, up to speed, so once it reaches its desired voltage, right? We measure the voltage coming out of the generator and the phase angle, right? And we also measure the AC grid voltage and phase angle. So if it comes within a certain range, if both the voltage and the phase angle comes within a certain criteria, then we close the unit breaker. So this is how we utilize this relay basically to close the unit breaker and integrate the generator to the AC grid. Next is under voltage elements, and that's device 27. Then directional power relay, I made mention, for reversal of power flow into the generator. Then a field relay, loss of excitation, so basically if you have, a field that's set up on the rotor winding, and basically you lose that magnetic field due to a problem with your excitation system or inaccurate measuring system, or let's say you have a VT failure, then that is when basically your magnetic field is going to change, and that's how this relay detects a problem with the excitation system and a problem with the rotor winding. Next is the field breaker. The field itself that provides DC voltage and current has a breaker that basically it closes in to basically provide the required voltage and current to the rotor winding. Next is negative sequence relay, right? Basically, it's let's say if you have a phase unbalance, and phase reversal, ANSI device 46. So this is what this relay does. It detects that amount of unbalance. So for each generator, the manufacturer specifies the allowable unbalance that is supposed to achieve for a period of time, right? So let's say a negative sequence unbalance, let's say 5%, 6%, 10%, let's say for a certain period. So I squared T, and it also provides a K, and the K number is basically a multiplier that is provided by the manufacturer. Next is instantaneous overcurrent. Basically, this is usually a backup for the main differential protection, and this is usually utilized in smaller generators, where there's no need to basically have a main protection scheme utilizing a differential protection. Next, it's time overcurrent relay ANSI device 51. So this basically has much more timing. It's not instantaneous and operates on an inverse current. Basically, it basically protects the generator based on overloading and onset of fault. Next is AC circuit breaker. So that's ANSI device 52. Then we have 52A, 52AA. Those are auxiliary contacts for the breakers. So for breakers that use high-speed contacts, basically we utilize 52AA and 52BB. Next is over voltage, and that's ANSI device 59. And for voltage unbalance due to a fuse loss, that's ANSI device 60. Then for ground for detection, we utilize 64. Then for frequency elements protection, we utilize 81, ANSI device 81. Then lockout relay. Lockout relay is ANSI device 86. Okay, so depending on the owner of this generating plants, right? Okay, so the owner can come up with a scheme, that basically from the output of these relay elements, I don't want to go straight to the breaker, into the breaker. I want to go through a lockout relay, right? So the lockout relay is the intermediary from between the relay and the breaker, right? So the lockout relay also is, has a multiplying contact, has a lot of, multiple contacts, that it trips other elements. So let's say you have a differential protection that sets in, right? It basically activates. Then that differential relay, it's basically wired to a lockout relay, right? So the lockout relay trips has a lot of contacts, right? It trips the unit breaker. Then it trips the turbine side valves, right? Steam valves. Then it trips the field breaker. So basically, what a lockout relay does is basically has that multiplying contact to trip other sources that are supposed to be tripped, in addition to tripping the unit breaker. Next is differential protection, and I made mention that is ANSI device 87. Next is a beautiful picture that shows you a damage to a stator due to a ground fault on the stator. As you can see over here, it's a big core damage, right? There's a damage in the core and basically a winding damage as well. So this is not pretty. So that's why you need all those expensive protection scheme to protect your generator. Another damage, but this time to the end bell area, end winding area. As you can see over here, these are the coils that come out of the end winding area and are formed in a Robel configuration. They call it a Robel, the way it is wound. So this is the end winding area, and that's where the fault occurred. Now let's talk about typical connections of the generator to the bus or the utility, right? So this is a direct connector. Typically, this has a low impedance. These are utilized in industrial, commercial facilities, and they are very simple, very inexpensive. Okay, so you can also have different grounding schemes on different generators. Let's say at an industrial facility or commercial facilities, you can have, let's say, 2 or 3 generators, and you can have one generator connected in high impedance, right? You can have one generator connected in low impedance, and you can have one generator connected in solidly grounded system, right? And no grounding in that part, on the neutral part, right? And you can have them all connected to a common bus, right? So these are usually used in industrial, commercial, and facilities. And basically, you can have problems of circulating current because of the different grounding scheme. So it is very appropriate that you have a single grounded scheme in such a connection. Then we'll talk about unit connections, and this is what is utilized by most of the generation facilities, generating plants. Basically, it's called unit connection, and it has a high impedance, as you can see over here. This is the neutral of the generator, right? And it's connected to this high impedance single phase distribution transformer. Basically, that sets up a high impedance path to ground. Then it goes to a step-up transformer through a unit breaker, so it has a dedicated transformer to it. This is a generator step-up transformer, and it has a dedicated grounding scheme that it has. These are mostly, like I indicated, utilized in utility power plants, and also for very large industrial facilities. And this is what is utilized. And it provides, I'll say, about 95% static ground fault protection, and you can utilize for the remaining 5%. I made mention that you can have a complementary protection by utilizing the 2017 third harmonic undervoltage relay. Next, you can have multiple high impedance connected generator to a bus and to the AC grid, where basically they are all connected through a single step-up transformer, right? Basically, you are saving costs through that, and also these are used in very large industrial and utility system, And for this one, since you have a similar grounding scheme, high impedance grounding scheme, there's no issue of circulating currents. If you were supposed to have a high impedance grounding here and a low impedance grounding here, that is when there's the possibility of circulating currents. Now let's talk about the types of generators that we have over here, out there in the world. Okay, so we have cylindrical rotor synchronous generators. These generators are very fast. Let's say your most common that I've seen is 3600 RPM. They rotate at a faster rate. And we have a salient pole. And salient pole synchronous generators are much slower. That is what is used in hydro power plants. But for gas turbine plants and oil plants, and coal power plants, this is basically most of them utilize a cylindrical rotor, and a steam turbine plants. They utilize a cylindrical rotor. And some also utilize an induction generator. We have induction generators utilized in wind farms. So this is a nice picture of a cylindrical rotor and stator generator. As you can see over here, basically, this is someone doing an inspection, performing an inspection of the stator core and the stator winding during an outage, right? As you can see over here, the rotor has been removed, right? So I used to do these inspections, many decades ago, when I was working at the Exelon and Emerald. Yeah, so basically, what the person is doing is, this is basically, about 1 month outage that, usually they take, so this is a major outage. For them to take the rotor out of the generator, that means like it's a major outage, So you have the generator engineer, or maybe the plant engineer, that has been trained how to do these inspections, basically, doing his inspections. So basically moving, from one end of the generator to the other end, basically inspecting each slot of the generator where the windings are located, and the end bell area where the end winding area, looking for heating and looking for damages to the core and to the winding and the insulation system. Next is a typical picture of a rotor, So as you can see over here, these are the rotor slots, right? This is where the windings go in. So the windings are embedded in the slots, as you go around the peripheral surface of the rotor. So basically you have this is a two-pole machine. You have a north and the south pole, magnetic pole, right? So the windings go into the slots all the way, and they are wound, basically, to basically achieve the required voltage that is supposed to, magnetic field that is supposed to create to induce that amount of magnetic field into the stator to create the required voltage. Next, it's a nice picture of a salient pole rotor and stator, right? Okay, so I told you that the salient pole type of generator is utilized in a hydro power plant, and because it has many poles, right? It could be 100 poles, 200 poles. The speed is slow, and basically that's what you need, for a hydro power plant that utilizes water, basically on the turbine side to basically create the required turbine energy to turn the rotor of this generator. Comparably to cylindrical rotor, basically has two poles, and two poles basically, it has a very fast speed, like 3600 RPM. So now let's talk about the typical grounding schemes that we have for generators. I think I mentioned briefly about the types of grounding schemes that we have, when I was basically elaborating on the different connections of generators to different buses into the AC grid. But now let's go deep dive into the different grounding schemes that we have. Okay, so we have an ungrounded scheme. Basically, if you have a delta scheme, it's ungrounded, or you can have a Y that is not, it's floating, it's not grounded. You can have a solidly grounded system. You can have a low impedance grounded scheme, medium impedance grounding scheme, and a high impedance grounding scheme. But most often than not, we have these ungrounded scheme, solidly grounded, low impedance, and high impedance. It's a medium impedance. Basically, in the US, it's not popular here. It's mostly popular in the Europe and the Asia region. So, as the name sounds for itself, basically, you have there's no connection for an ungrounded scheme. There's no connection between the neutral and ground of the generator. So basically, the neutral is floating. So because of that, you have an embedded, inherent phase to ground capacitance, from the generator and the transformer winding, and basically, that helps to limit, high impedance ground faults to very, very low values. So it's very difficult because of the, the ungrounded nature, to detect ground faults is very difficult. So you have to come up with a scheme to derive grounding detection for this. So a phase to ground faults are basically results in the shifting of the neutral. And the unfaulted phases basically see much more of a face-to-face voltage. Okay, so next is a reactance grounded scheme. So basically we are utilizing a reactance to limit the amount of current, ground fault current. So for a solidly grounded generator, right? As the name says, basically we don't have any resistance or reactance in between the neutral and the ground, right? Okay, so basically, the ground, if a ground fault should occur, it is only the generator impedance that limits the ground fault. So because there's no zero sequence impedance, the ground fault can be very large indeed, because there's nothing on the neutral to limit the ground fault. So basically this can cause a lot of damage to the generator, especially for large generators. So most often than not, solidly grounded generators are utilized for very small generators, very small generators, non-critical generators. Next is a high impedance grounding scheme. So I've already made mention that we utilize a single phase distribution transformer at the neutral of the generator. And basically it goes through tens ratio to basically limit the fault current between 5 amps to 20 amps, typically about 15 amps. Next is a typical picture of a low impedance grounded scheme. As you can see over here, our goal is basically to limit the ground fault to 400 amps. So that 400 amps should be good for enough for this generator in an industrial facility. Next is another picture of high impedance grounding scheme. So as you can see over here, this is the single phase distribution transformer, right? So on the secondary side is a resistor that basically is connected across the secondary winding of this distribution transformer. So across that is your 59 G or 59M relay, ground over voltage relay. So basically it's detecting over voltage condition across this resistor to determine a ground fault condition in the generator. Next is we can also have a hybrid impedance grounding scheme that utilizes low impedance grounding scheme, a combination of a low impedance grounding scheme and a high impedance grounding scheme. So when the generator is in operation, right, it is connected. You have a vacuum switch over here, right? Basically, so the generator is grounded through this low impedance grounding scheme. When there's a fault, right, the 87 differential relay detects that fault and basically trips this breaker quickly and basically opens the switch so that the generator can be grounded through this high impedance path to limit the current flow into the generator. Now let's talk about fault classification in generators. We can talk about internal faults and abnormal operating conditions in the generator. Okay, so for internal faults, we can have face-to-face or line-to-line faults in the generator. We can also have face-to-ground faults. We can have double face-to-ground faults. We can have three-phase voltage faults, and we can have roto-ground faults. And all these are basically, a lot of them is due to insulation failure, core damage, and also deterioration of the insulation with time, right? And this can be attributed to mechanical vibration, environmental conditions, and also external conditions from lightning that can cause those damages. Then we also have abnormal operating conditions, that is over voltage, under voltage, overfluxing, over excitation. Then we can have over frequency, under frequency, loss of excitation, inadvertent energization. Inadvertent energization basically occurs, let's say, you have an outage, right? And you have a generator that has been disconnected from the grid, and the generator is on a turning gear. That is, you have when usually during a minor outage, right? When the generator is not, the generator rotor is not taken out, and the rotor is put on a turning gear, so it turns very slowly. Because what it is the rotor is so massive and it is warm, right? So if you don't continuously put it on turning gear and turn it slowly, well, basically the rotor is going to bow. It's going to start bowing and shake, and basically can create a vibration problem. So that is when the rotor is put on 10 gear. So if you have, let's say, an operator, that goes into the switcher and, inadvertently, closes, the generator breaker, basically what is going to happen? The generator is going to be energized, and there's going to be a backflow of reverse power, right? And it's going to motorize the generator. So inadvertent energization, anytime there's an outage, right? Be it minor or major, this relay is energized, to basically protect the generator from accidental energization. And basically it operates based on 50 and 27 relay combination. That is instantaneous current and under voltage condition. Because when you energize the generator, the voltage is going to be very low. It takes a little bit of time for the voltage to build up, right? Okay, but the current is going to be high. Once you energize, the current is going to be high. So it measures that and basically determine that we have an inadvertent energization. And basically what it's going to do is basically trip any breakers that are supposed to be tripped. Then we have loss of prime motoring, and that is when you have reverse power, right? 32 basically flows into and basically motors the generator. Then out of step condition, that is ANSI device 78, right? Okay, so if you have a generator that is, as you can see over, the AC grid has many transmission lines that are interconnected. So you have, let's say, thousands of generators, or modify that. Let's be realistic. We have about, let's say, 200 of generators that are all interconnected to many transmission network, right? Okay, so if you have a generator, right, that has a fault that basically cascades, and that generator is not able to recover, and basically the fault is not able to be isolated, and basically the generator, isolated from the rest of the generators, right? Basically, there's something they call out of step, right? The generator is going to lose synchronism with the rest of the generators. So that is when the out of step relay comes into play, right? To be able to finally trip the generator, and if any other generators that might be affected, basically it trips it. Next is overload condition, let's say, and that is based on 51, and blown fuse for the VT and open fuse for the VT. And winding thermal protection is, let's say, if you have excessive heating in the winding, be it in the stator winding or the rotor winding. So we talked about differential protection, right? Okay, so that's types of protection. We've talked about different abnormal conditions that could occur. Now these are the types of protection that we can have for a generator. 87G, differential protection, state over current, 5051, and loss of excitation, negative sequence, when you have a reversal of phases, then reverse power. Basically that can be graded into different states, 32-1, 32-2, based on the timing, right? So 32-1 is graded for a certain time. Then if the reverse power continues to flow, then 32-2 is usually what trips all the required breakage. Then out of step, I think we did mention about that. Then a 51 voltage control over current. This is basically a backup for remote faults. Then overfluxing condition, and that is ANSI device 24. Then state of ground over voltage, that is ANSI 59 with a complementary third harmonic that protects 5% of the remaining neutral winding. Then also for ground fault protection, we can use another. If we choose not to go with this protection philosophy, we can go with a harmonic current injection. Basically, what it does is it injects harmonic current from the neutral, and basically measures the voltage. Based on that, it's able to determine whether a state of ground fault has occurred or not. So, and also, high impedance ground fault. So this acts as a backup for the 59G. If the 59G should fail, then this becomes the backup relay for state of ground faults. Then for low impedance grounded schemes, usually in industrial facilities, the state of ground fault utilizes the instantaneous and time over current neutral over current relay. Then rotor ground fault is 64F and also 87 for overall differential protection. Then under and over voltage protection is 2759. Then over, and the frequency is 81 U or O. So now let's talk about which sections of the generator turbine that all these protection schemes and abnormal schemes that I've talked about. Okay, so for reverse power and frequency, it applies to the turbine. So that is why these turbine manufacturers gives you a chart, that basically shows you all the operating allowable frequencies that you're supposed to have, and if you go beyond that, how long you're supposed to have that. And also reverse power applies to the turbine. That's when the turbine steam valves are basically shut off, closed, to prevent basically the turbine from spinning based on a reverse power, and the generator is moving at that instant. So negative sequence unbalance applies to the generator, right? The loss of station applies to the winding, the rotor winding. Then pole slipping also applies to the rotor winding. Then rotor ground fault applies to the rotor. Then thermal overload on the rotor applies to the rotor. Then for the stator, we have a differential, right? That we can have overall and generator differential. Then over voltage applies to the stator. Then overfluxing applies to the stator. Then thermal overload of the stator applies to the stator. Then also voltage restraint, and step distance, applies to the stator. Then stator ground fault applies to the stator. Then accidental energization, that is inadvertent energization during outage, applies to the stator. So this is the end of the first session of generator protection. So next time we'll basically continue this presentation of generator protection with the second session. Like I told you that the number of slides is getting close to about 600. So basically, I have to break it into about 10 sessions to make it easier for you to absorb the material and digest the material. Thank you.